Hey guys, welcome back. So today we're going to be talking about chemical equilibrium. So far, we've only considered reactions that go to completion. Um, this isn't always the case. Some reactions will go to what we call equilibrium. And this is a dynamic equilibrium, meaning that although there is no net change, there are still collisions that go from product to reactant and reactant to product. It just so happens that the rate of consumption equals the rate of production, and hence there is no rate, and we reach equilibrium. When we go to completion, these here go to zero. However, at equilibrium, not everything goes to zero. Reactions typically get slower over time, as explained by the collision model. Basically, since you have reactant particles that collide, you have the forward reaction, which is just two particles collide to form the product. That's the forward collision. However, the backwards collision is, say you had two products and they collided with enough energy to just sort of bump into each other and decompose both of them into reactant. So that's sort of the idea here. Um, the slopes of so when we go for completion, these lines here go to zero, and one of the reactants goes to zero, clearly. So that's sort of the idea there. Now, what if we go to equilibrium? Um, these lines here they'll obviously be flat. However, they won't. None of them will be at zero. There will always be some concentration of something. Now, when we talk about equilibrium, we should first quickly define what is an open and closed system. Uh, to express it within the context, the system is the set of related reactants and products within a container, and if it's closed, there is no exchange of matter or energy between the systems and the surroundings. So, gases in a rigid sealed container would be a closed system, where as an open system is where matter and energy can exchange between the systems and the surroundings. So, an uncovered beaker um, involving a gaseous product that escapes would be an open system. Now, most equilibriums that you'll encounter generally tend to exist within a solution, so they're aqueous, and therefore the water is the system, and they behave like closed systems, even though technically it's considered an open system. One sec, my phone keeps unplugging here. Characteristics of reactions that go to completion is that there's zero rate, one reaction concentration ends up being 0 molar, and they typically happen in open systems where the products can escape. Now, if you close the system, you'll get equilibrium, since there's nowhere else for the particles to go but stay where they are, and then eventually as a result of time, once you build up enough product, the only thing that they can do is say the products hit each other and you form the reactant again. Uh, Reverse rate in the study kinetics. It's rarely consistent with time, and it depends on the concentrations as the higher levels will know. And kinetic studies are done in such a way to avoid this. And this is why when you study kinetics, you have to try and really be careful here. And I talked about it with the higher levels, but for the standard levels, you need to know that generally kinetic studies are usually done in such a way to prevent or avoid the reverse reaction. Um, so here's sort of a system that reaches equilibrium, and as we can see here is that R is the big dotted line and P is the small dotted line. We can see here that they both reach half a molar of concentration. And notice here that the rate is zero since the slope is zero. This is a system that has reached equilibrium. And this is already talked about, but here it's worth just reiterating again. My God, words. The forward rate gets progressively slower, and the reverse rate gets progressively faster, and then the overall rate is here, 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 and there's zero overall rate because the rate of consumption is equal to the rate of production. Chemical equilibrium is defined as the state at which there is no net reaction, however the forward and the reverse rates are equal to each other. It's a dynamic process, and there is still production and there is still consumption. It just so happens that they happen to occur at the same rate, so therefore it is considered an equilibrium. You'll use this sort of half arrowhead thing here to denote equilibrium. Instead of this arrow here, you cannot use an arrowhead here because that's usually what we use to denote resonance structures. It's just notation you have to get used to. And then chemical reactions that reach equilibrium happen in closed systems. Rates are zero. I've already talked about this before, but here's a more complicated case. Notice here how there's always something, um, but there's no rate since the lines are flat. So equilibrium is all over the place. However, something that we note here is something called the equilibrium constant. Okay, so now we know that something exists in equilibrium. Can we use this to quantify or do something with it? And the answer is yes. Note that here we have something called the equilibrium constant, which is just it's a measure of the amount of products to the amount of reactants within a given system. That's sort of the way I like to think about it. More formally, for the higher levels, it's actually a bit of the rate expression. It's a bit of the rate expression, and it actually does correlate to rate. It does correlate to rate for the higher levels that have seen this sort of thing. It's the rate of production or the rate of consumption, more or less, with the rate expression. But you can just think of it as product over reactant, and the reaction is so given here for this hypothetical reaction. It's the concentration of C to the power of its stoichiometric coefficient, which is this little c, times the concentration of D to its stoichiometric coefficient over A to its coefficient and B to its coefficient. And Kc is called the equilibrium constant, which is specific for a given which changes with temperature, and the concentrations are measured in molar. So to form an equilibrium expression here, we have this given reaction. We put products over reactants, so the concentration of this squared, since this 2 here, that's the coefficient. Since there's no 1 here, it's implied to be 1, so it's O2 to the 1, and it's NO2 squared over. The units of Kc depend on the reaction, and you can just derive it using dimensional analysis. It really doesn't matter if you memorize it or not. The equilibrium constant for a given temperature for a specific reaction is always the same. The only thing that changes the equilibrium constant is the temperature, is basically the point here. The size of Kc relates to the tendency of a reaction to occur, but it does not relate to the rate of reaction. When Kc is much larger than 1, the equilibrium is generally it's shifted towards the products, and if Kc is very big, the reaction is towards the products. If it's very small, it's more biased towards the reactants. And you can see this here, that if you increase this numerator here, you get a larger number here, whereas if you divide by a smaller number, if you divide by a bigger number here, which indicates the reactants, you get a smaller number here. That's sort of how that works. It's just math. Lastly, an equilibrium position is a set of concentrations for a system at equilibrium. It's just one set of numbers that just happens to give you the equilibrium constant. So say, for example, so these numbers here get you to the equilibrium constant, as do these numbers, as do these numbers. If you double the coefficients, you square it. If you multiply by some constant, you raise Kc to that nth power. And the way you could go about doing the reason that works is because if you double these coefficients here, so 4 is 2 times 2, 2 is 1 times 2, and then H2 is 3 times 2 for this equilibrium here. Since you double those coefficients, you can factor out the 2, and you get Kc squared. And if you reverse the reaction, you inverse Kc. You just take the reciprocal of Kc. And that also makes sense because, if you reverse the reactions, if you reverse it, you put these here and those here, which happens to be the inverse of Kc. So, yeah, thank you very much.